Hi, in this lecture video, I will be discussing an oxidative cleavage of an alkene that is known as ozonolysis. So this is another type of addition reaction of alkene in which that it completely break the carbon-carbon double bond in the alkene in two steps. So again, the carbon-carbon double bond is completely split apart, and now they would then be converted into the two carbonyl groups. For an example below, when we take this alkene right here and we do ozonolysis on it, ozonolysis consists of two steps. The first step is called the oxidation step by using O3 or ozone, and followed by the second step with DMS, stand for dimethyl sulfide, and this is the reduction step right here. So first is the oxidation with O3, the second is the reduction with DMS. And the product of this reaction is when we will be able to cleave this carbon-carbon double bond and put in an oxygen on each of this carbon right here. So now they become two carbonyl. So this will be the product of this reaction right here. And so now let's go over the mechanism of this reaction a little bit. So first one is the oxidation with ozone. The chemical structure of ozone is as follows. So here in this case right here, we will then see as follows. So here the chemical structure of O3. And now when O3 come in to interact with the alkene, this is what happening. Again, we have seen already that an alkene can be a weak nucleophile. And therefore, when it come in to interact with ozone, it actually is attacking one of the oxygen in ozone. And the reason why that happened is as follows. Here in this case right here, we can see that one of this oxygen right here, is an electrophilic oxygen. And the reason why that happened is as the electron come over here to this oxygen here to form resonance structure. This oxygen right over here will no longer have an octet of electron, and it will then become a positive charge. So we have an oxygen that in one of the resonance structure that it does not have an octet of electron and a positive. So therefore, it is a good electrophile. So therefore, the double bonds, the pi electron from the alkene come in to attack this oxygen right here. So that is the explanation why that it come in to attack this oxygen. And that once this come into attack already, the electron is again given to this oxygen. And now one of the other carbon here will become a carbocation once the alkene is attacking the other oxygen. And now the other oxygen over here is negative. So therefore, this is a good nucleophile, and that will then come in to attack the other carbon. So in the end, we'll be forming this product right here. And this is something we call an ozonide. And this ozonide right here is not stable. So what happens is that it will then break apart. And this is how it be broken right here. So first, the electron for the oxygen come in from this oxygen donated in, and then that is exceeding the octet for this carbon right here. So therefore, to liberate that, this carbon-carbon bond is been broken, and the electron is then donated to the other bond between the carbon and the oxygen, and this oxygen then take the electron and give it to the other oxygen again. So in the end, this is what we're getting after this step. And once we produce this step already, this is still not stable. So basically, this oxygen come in to attack this, and this go back and attack this carbon again, and we form this ozonide. So the product of this first step right here is this ozonide right here. And once we have produced this ozonide already, it is not something that we can isolate easily. So therefore, we have to follow with the reduction step pretty much immediately. And that it can be achieved by using dimethyl sulfide or zinc in water. So this will be the reducing reagent right here. So when we react this ozonide with either this reagent right here, it will then be reduced, and now we'll be able to convert this back into the carbonyl here and the carbonyl over here. Now the mechanism of this reaction right here is quite complex, so therefore we're not going to be discussing its mechanism. Okay. And now let's try some of this reaction right here. Predict the products for this reaction when this alkene right here are first reacted with ozone followed by reduction using DMS. So here in this case, knowing that this is a ozonolysis reaction, we'll be able to cleave this carbon-carbon double bond and this carbon-carbon carbon double bond as well. So all carbon-carbon bond will be broken in that process, and we'll be able to convert this into the carbonyl group. So here in this case right here, we'll be able to break this bond, so we'll be able to have that as become a carbonyl. And now over here, we'll be able to break that, and this become a carbonyl as well. And then on the other carbon, there will be a carbonyl right here, and that will be that first product. And the other product would then be the other molecule over here, this segment over here, that now become its own molecule. And now there's a carbonyl in it. So that will be the product of this reaction right here. The organic molecule is now broken up into smaller organic molecules. And similarly with some of this example right here, if we were to do this, then again we'll be able to cleave right here and right there. And if we were to do it with C, we'll be able to cleave them right there. So basically we're able to convert this into 2-carbonyl. So quite easy to predict what will be the product of this reaction. And same thing in all of this. So in this reactant D right here, they will be getting this product right here. So that will be the product of this reaction. And now this can become an aldehyde. So they can either become aldehyde or ketone depending on the substitution on the starting alkene. If the alkene have two substitution group on it, it would then become a ketone. Versus if you have only one substitution group, one alkyl group on it, it would then become an aldehyde. Okay, so the product is then determined by the structure of the starting alkene.